Yes, okay, thank you, Mathieu, for the introduction. So yeah, my name is Philipp Tuchen. I just started at NOAA AOML, working with Vanellis Paris and Greg Falls on something different. So I'll be working here on long-term variability of tropical instability waves. But I thought it would be a good opportunity to introduce myself in this the kind of seminar and to show some work from my previous position, which I did together with Peter Brandt, Joke Lübbecke, and Rebecca Hummels back at GEOMA. So yeah, it's a paper that has been just recently published, and if you want to take a shortcut, you can scan the QR code here. But obviously, I will also talk about it today. So I'm just gonna get started. Okay, I want to start with the with this AMOC schematic from Boa et al. In 2019. Of course, you know that the AMOC is the Atlantic Meridional Overturning Circulation, and in this schematic, you can see the two different branches that are associated with the AMOC circulation. So on the one side, you have in blue lines, you have the transport pathways of cold water going southward at depth. And then in the red lines, you can see the return flow, or the warm water returning to the North Atlantic seas and the Nordic seas, intensified in the upper part of the ocean. Of course, the AMOC is always associated with a huge amount of meridional transport of heat, of salt, of carbon, of other relevant tracers, and it's therefore estimated to be a crucial component not only of the North Atlantic climate, but also of the global climate system in general, and is often referred to as a tipping point or as a tipping element of the future climate. So I'm focusing now on the tropical part of this AMOC schematic, or of this AMOC circulation, and especially in the tropical Atlantic, you can see that both branches are basically on top of each other and very concentrated at the western boundary. And in fact, the western boundary circulation in general in the tropical Atlantic consists of three components, which are the thermohaline circulation on the one side, and of course the wind-driven circulation on the other side, which then further consists of the subtropical cells, or the STCs, and also a compensation transport for the interior sphere drop balance. And especially this superposition of these two components, the THC and the STCs, is quite interesting to observe in another schematic view, which I'm going to show you now. So just think of this as the tropical Atlantic. Just here you have the depth, and just from the southern subtropics to the northern subtropics on this line. And we divide the tropical Atlantic upper ocean into two layers. So on the one upper side, there's the surface layer that is influenced by the wind stress, and then at subsurface level, we have the thermocline layer, or also called the STC layer. As you all know, the dominating wind pattern is the eastern easterly trade winds at the surface, which are then exciting poleward Ekman transport in both hemispheres, initiating this subtropical cell circulation. Then in the subtropics, we have the subduction of water masses, basically in the subtropical gyres, and these water masses are then brought back to the equator or the equatorial regions by geostrophic transport at thermocline level, and eventually the cells are closed by equatorial, but also by eastern boundary upwelling. And this is basically all the four different branches of the subtropical cells for both hemispheres now. What I also would like to point out is that there's also geostrophic transport observed in the surface layer, which is then counteracting the overall Ekman transport divergence. It's not compensating it, but it's definitely reducing it. So yeah, this is something I always like to point out, and yeah, must not be forgotten. So then on top of this STCs, as I said, we have the thermohaline circulation, which I just schematized here. What is known is that thermal circulation is coming from the southern hemisphere, that is still more a subsurface intensified flow, which it's not the case once it is reaching or exiting the inner tropics at the northern hemisphere. So there is then a surface intensified current. So you have definitely some upwelling of these water masses within the tropical or equatorial regions. One thing that is also becoming obvious from this superposition is that these this combination of flows of DHC and SCCs lead to are supporting each other in the southern hemisphere, so having the same sign. But then in the northern hemisphere, the DHC is counteracting the geostoric transports, and this leads to an overall asymmetry of both hemispheres, which I will be showing also in a few slides, but just to show them to you in a schematized way. Okay, so this is now just a two-dimensionally or zonally average two-dimensional view of the cells, but of course it's not so easy in real world. And yeah, okay, sorry, I forgot this to mention. So this transport then, or this upwelling, is always associated with some kind of water mass transformation when we observe this diapical transports. Okay, but now coming to a more horizontal view on the subtropical cells. This is also probably one of the most famous schematics of the subtropical cells, going back to a paper or a review paper from Schott et al. In 2004. And just showing you basically what I've showed you before, but now in a more horizontal way. So again, we have the Ekman transport in the surface, originating in the tropical or equatorial bands, and then leading to this poleward, westward transport of water masses at the surface. Then we have these subduction areas along the equatorward branches of the subtropical gyres, so the NEC and the SEC. And what is maybe most interesting in this plot is the different pathways of geostoric transport at thermocline level. So basically, what is shown here are two pathways. So for one, the western boundary pathways, and then on the other side, the interior pathways, also accounting for the interaction with the zonal current system here in this zigzag pattern. In principle, there's also a third possibility for subducted water besides the western boundary pathway and the interior pathway, which is for the case when they are reaching the western boundary too far south, at least in the case for the southern hemisphere, too far south of the bifurcation area of the SCC. So then these water masses are just, or water parcels are just recirculated within the subtropical gyre and do not participate in this overturning circulation associated with the SCC. Okay, but yeah, keep in mind there are two different pathways, interior and western boundary pathways. Also shown here are transport numbers associated with these different pathways from a study by Zhang et al. In 2003, which was based on hydrographic data. So they produced a mean estimate from data between the 1950s to 1990s. And because these data that were before the Argo program started, a big part of my PhD work was actually to revisit these STCs from an observational perspective, and including now the Argo data since the early 2000s. And yeah, just before, don't want to forget the last part of the cells, which is the upwelling that you can see here in the eastern boundary upwelling systems, but also along the equatorial undercurrent or the equatorial band in general. Okay, so now coming to a few results about the subtropical cells, to just give you a bit of background information and to lead to the current study. So what I did was I separated, or I estimated the subtropical cells, the two horizontal branches, which are the thermocline layer geostropic transport and the surface layer Ekman transport. So I used a mean from an Argo climatology, the Ramesh-Gilson climatology, with a 1 degree horizontal resolution, which is shown here in this plot. And here it is important to note that all the red colors are indicating equatorward transport, and the blue colors indicate poleward transport. So just to illustrate the convergence of mass of transport in the thermocline layer. So there are two things that are striking in this plot. First, we definitely have a concentration of transport at the western boundary. So in both hemispheres, it looks like these transport pathways are the dominant ones. And then there's also a big difference between the interior pathways in the northern hemisphere and the interior pathways in the southern hemisphere. So in the southern hemisphere, you can see this connection all the way from the subtropics to the equatorial regions, which is not present in the northern hemisphere. So this is also a well-known feature of the northern hemisphere, where a potential vorticity barrier in the eastern part of the northern Atlantic or northern equatorial Atlantic prevents the subducted water masses to find an interior pathway. So they are rather deflected, or they have to take a westward detour and then join the western boundary pathway. This also leads to this mentioned asymmetry between the two different cells in both hemispheres. Okay, and then one thing that we noticed when we were doing this analysis was that when we are now just looking at the 10 south section here, and then looking at every grid point and adding the transports from the eastern boundary to the western boundary, which is shown here in this graph. So for different products, so in black now, that's the Argo data that is shown here. We also did this for the AMOC climatology and for the OS4 reanalysis. But what we also did at the western boundary, which is located here, westward of 32 West, is that when we are adding transport results from a repeated ship section along 11 South, we can see that the difference between western boundary transport from Argo and western boundary transport from the ship section is about 2 sphere drops. So it's really looking like there's a considerable difference between estimates from Argo and from observed or ship-based measurements at the western boundary. So we concluded that there's still some the Argo data is still struggling to reproduce the circulation at the western boundary, and it has to be taken with caution. And just to show you the upper part or the upper branch of the subtropical cells, this is now Ekman transport calculated from zonal wind stress from the SCAT data with a 1/4 degree horizontal resolution. And again, blue means poleward transports. So you can clearly see, due to the easterly trade winds, this component induces more or less everywhere poleward Ekman transport. Only in the most eastern part of the 10 North section, you have some southward or equatorward transport. But in general, it's a very, very symmetric Ekman transport divergence in the upper layer. Okay, and it's maybe worth to mention that the surface layer is defined as roughly the upper 60 meters, and the thermocline layer is defined below and down to about 200 to 300 meters, which is equivalent to an isopycnal boundary. But due to the shoaling of the isopycnal towards the east, this is a range of depth. Okay, and then we summarize all the transports that we calculated at the sections at 10 South and 10 North. So again, see this as a schematic of the tropical Atlantic. There are our boundaries of the surface layer. As I mentioned, this Ekman depth, which is roughly at 60 meters, and the lower boundary, which is the isopycnal. Right, and then we just used all the data that we could find. We estimated the Ekman transport, which is quite symmetric, reduced by the surface layer geotropic transport, estimated by Argo data, and this leads to a net transport divergence of 14.6 sphere drops. So now for the thermocline layer, we did the same. We divided the transports at both sections into a western boundary and an interior transport. For the southern section at the western boundary, we decided to go with the ACP measurements to account for this underestimation of Argo data there. Right, and then you can also see that we have this asymmetry of around 9 sphere drops from the south at thermocline level and around 3 sphere drops from the north. So basically, at thermocline level, the southern hemisphere is three times southern hemisphere SEC is 3 times stronger than the northern hemisphere STC at thermocline level. And all these transports add up to around 12 square drops of thermocline layer transport convergence. And if you're now comparing these two transport balances, you can see that there's some residual. And we tried to discuss this residual and found 2 different possibilities. So the first one would be just like at 10 South. At 10 North, we don't have any comparable ship-based or repeated ship section that we could use to compare these results. So there might be something that we are missing at 10 North. But then on the other side, what we might miss very close to the western boundary would only be northward transport. And a northward transport would reduce this transport here and would reduce this transport and would in total increase the residual. So we thought there must be also something else. And what we think, or what we assumed, was that there must be some transport coming from below. So just some diapiconal transport that we are not measuring at 10 South and 10 North, that is entering these layers in between these 2 estimates or 2 attitudes of estimates. So this is now the motivation for the study that we did. We wanted to quantify and revisit this value from Argo data. And a bit of background why we want to do this is because there were so far not many studies, but basically 2 main studies, I would say, that already dealt with this value. There's one famous one by Römmich in 1983, which was based on 5 ship sections in the 1950s, and they used these sections to define 8 different layers. And one of the main points of this paper is then that they find about 6 sphere drops of layer 2 waters, so very close definition to what we defined before as the lower boundary of the thermocline layer. So 6 sphere drops are going across this boundary, this upwelled, and then converted to layer 1 water. So they're called it surface water, and then swept northward. So many studies in the afterwards, they relied on this, or they always included this part of the upwelling in their STC estimates. And then there's another one by Lux et al. In 2001. Also, they had 2 sections, one at 7 North and one at 4 South. And they used a bit of different definitions for their thermocline and surface water, so it's not that comparable, but nevertheless, they estimated around 7.5 sphere drops of thermocline water upwelling into the surface water. So quite, if you remember the transport estimates of the different branches of the SSCs from Argo, these numbers that are showing here, they are quite high or quite considerable when looking at our total budget. So yeah, we wanted to understand this and wanted to repeat these, or revisit and quantify this transport now based on Argo data. And what we're using now is a Argo mean fields, just one mean field, also from Römmich and Gilson, which is available on a 1/6 of a degree grid. So before it was always a 1 degree monthly varying field, but now they also provide a high resolution mean field. And the first thing, because we saw the 1 degree product had its problems with representing the western boundary circulation. So first thing we did was to validate this high resolution product against repeated section data at 11 South. And this mean section is now shown here, just showing the meridional and alongshore velocities along 11 South based on 12 different sections between 2000 and 2019. You can nicely see the 2 branches of the AMOC, in fact. So the northward part, which manifests in the North Brazil undercurrent, and the southward branch at deep water layer, which is the deep western boundary current. You can already see that we are using, or we divided this section into different water mass layers, which are shown here, or the definitions of these layers are shown here. We are basically following definitions from these 2 papers by Schott and Hummels, which were also using the same kind of data or an earlier version of this mean data. The only thing we changed was we divided the surface layer and this thermocline layer into into these layers that we have defined before for our SDC estimates. So in total, it doesn't make a change when we're looking at the overall AMOC return flow, because these two layers are just within this return flow, but it helps us to separate the SDCs more thoroughly from the rest of the water masses. Okay, so yeah, so this is the definition of the AMOC return flow, just basically all the water be above the interface between intermediate water and North Atlantic deep water, which is this isopycnal, which is roughly around 1,200 meters. Okay, and then we looked into what Argo data is showing us. So just to give you an outlook what we are using. So at 11 South, we have this repeated ship section here. We defined our 11 South and 10 North Argo sections, which are shown in these gray black lines, and which are divided into a western boundary, interior, and eastern boundary subsection. You can see that at 11 South, as I showed you, the upper ocean is dominated by the MBOC, which is a subsurface current that becomes a surface intensified current once it reaches around 5 South. And due to the complex circulation and the tropics, we also will be looking at different sections within the tropics and also equatorial crossing sections, which is quite important to include, because Argo data and geostrophic data it's not easy to, or not possible to retrieve from at the equator. Okay, yeah, as I mentioned, there are 3 different sections that we were looking at at the later part of this study. But first, we are focusing on the western boundary at 11 South and the comparison between Argo and ship section. So this is shown here in this plot. So it's showing the meridional transport as a function of neutral density. So basically, transport that is per density bin divided into different layers, or the different boundaries are shown here for the different water mass layers. And in yellow, we have the ship section data. In the red colors is the low and high resolution Argo data at 11 South. And in the more grayish, blackish colors, the estimates at 10 North. So first, focusing on the ship-based estimates, we can again see the structure of the AMOC, northward transport in the central water to intermediate water layer, and then this southward transport in the deep water layer. And yeah, you have to know that Argo data is only available to about 2,000 meters widely. So this is why only for the ship-based measurements we have data down to the bottom, and we will not be looking further into deep water or bottom water layers. But coming to the return flow layer again, you can see that at 11 South, the low resolution product is largely underestimating what we are observing by ship measurements, and this difference is now greatly reduced when we are using the high resolution product, which is a bit shallower. So the core is a bit shallower, but overall the structure is quite well reproduced. So this we were quite excited about this outcome. At 10 North, it's a bit difficult because we see some underestimation, or at least we can think of it as an underestimation of transport by using low resolution products, but we don't have any comparable reference there. So it's a bit hard to say what's the truth there, but it suggests that there's also an underestimation of transport by low resolution products. Okay, and just interestingly to show it's at the interior part of the section. So this is just to remember these huge subsections of the 10 North and 10 South or 11 South sections. It's interesting to see that there's not a big difference between the high resolution and the low resolution products. And this is quite a relief for previous estimates, showing that it's really not so dependent on the resolution in the interior, but the more crucial it is on the western boundary. Yeah, so that was also nice to see. Okay, and then putting real numbers on these layers, real transport numbers. So we just integrated the transports shown in these different water mass layers, which are shown in these bars here. Again, for the ship section, low resolution products in black, and the high resolution product in gray. And we added a Ekman transport in the surface layer, which we only applied to the Argo data, because the ship-based measurements, they assume to include this Ekman component already. And we even, for the upper part of the ship sections, which is not well covered by ADCP data, we included the mean velocities from surface drifter measurements. So these should also include the Ekman transport component there. We can see that basically at all layers below the surface, South Atlantic water is entering the tropical Atlantic, and agreement is great between Argo data, high resolution Argo data, and ship-based measurements, which reflects here in these total transports, which are very close. So about 21 to 22 sphere drops are entering the inner tropics at 11 south at the western boundary. So when we're now looking at what is happening at 10 north at the western boundary, we have this, first thing that strikes us that it looks like we have an absence of tropical cell and central water, but it's actually just a compensation of the transports there. So the western boundary transport is compensated by the retroflection largely. And what is interesting is that you can see on the one side around 22 sphere drops are entering the tropics at the western boundary, but only 12 sphere drops are leaving the tropics at the western boundary. And this already gives an indication that there's definitely more pathways for these water masses than only the western boundary. So the water must be leaving the tropics also at other parts. And just showing this kind of obvious upwelling already. There must be some straight pathways for the intermediate water. Then especially these two water masses are largely upwelled either at the during their path through the tropical Atlantic. Okay, and now coming to the first main result that we found. So this, as I mentioned, the initial motivation for the study. We just now repeated the analysis before, but now covering the whole basin. So we integrated the transports for each layer at both sections across the whole basin, and also including now again the Ekman transport at the surface across the whole 11 south and 10 north sections. So what we then did, what you can do is, under the assumption that in each layer volume must be conserved, you can start building balances for each layer. So I'll give you an example. What we did for the surface layer is now we take the geostrophic transports from Argo data here and reduce them by the Ekman transports in the surface layer, and this leads to an overall divergence of 11.8 sphere drops for the surface layer. One thing that we included was the freshwater input, so just precipitation, evaporation, and river inflow, which is about 0.3 sphere drops. And then in total, what is missing is the value of 11.5 sphere drops. And this is now must be supplied by the layer below. And we can continue these calculations further downward. And we also did this for the low resolution product. And the interesting numbers, or the numbers that we were looking for, are these two. So these are now our estimates from Argo data of how much water is upwelled, or how much diapical transport we can see into the STC layer. When you look at the low resolution result, that is quite similar to what has been mentioned by Römmich et al. Or Römmich in 1983, but the high resolution product shows only about a third of the same value. So it seems like the resolution also plays a role for the diapical transport, and this is definitely something something that has to be mentioned when doing these SCC estimates. Okay, to put this a bit more into context, again, looking at the Zhang et al. Study in 2003, it's a similar schematic showing you the both subtropical cells in the black lines and the superimposed THC upwelling in the gray line. And these 16 spherotrops that you can see at this point here, they actually, what they did was they estimated 10 spherotrops due to the SCC, so 6 from the western boundary, 4 from the interior part, and then they added these 6 spherotrops, which were mentioned by Römmig. So just because Römmig published these numbers, and yeah, so we are now basically questioning this upwelling or this upwelling estimate by Römmig. So there's also another study by Hasenleger and Dreifout in 2006. Basically the same schematic, a bit more complicated, but also entering 16 spherotrops, of which 6 are just not interacting with the subtropical cell and cells, which are shown here in these circles. Even 4.5 are subducting, and what is left is these 5.5 spherotrops of THC upwelling, which they also compared to the Römmig values and said they are quite in good agreement. So so definitely a few studies that are relying on these estimates by Römmig, and we are just now providing a different value and sort of questioning this previous estimate. Okay, and then for the last part, because we were quite happy with the agreement of Argo data and ship-based measurements at 11 South western boundary, we wanted to extend this analysis to the whole tropic Atlantic and to give more insight or a more or less coherent picture of observations on these different pathways and transport estimates at all the different sections that we used. Because what we can, first we can say to the circulation, what is happening to the North Pacific current. So once it is surface intensified and becomes the MBC, it crosses the equator and becomes unstable at some point. One consequence of this is that it sheds MBC rings to the northwest, which are then crossing our section at 10 North, and together with the NEC, they are pushed into the Caribbean and follow the western boundary AMOC pathway. Another consequence of the unstable MBC is that it retroflects back into the tropical Atlantic, supplying the North Equatorial countercurrent with surface water and supplying the equatorial undercurrent with thermocline water. So this is why, besides the western boundary pathway, there's also some more complex pathway, which is often called the indirect route of the return flow, which involves this recirculation into the tropical Atlantic, possibly also recirculations within the tropics, and then at some point it must be the water is removed from the tropics by Ekman transport at the surface. So this is why we are now also looking into the interior part here with these meridional sections. And these further additional meridional sections are shown here. Again, these are mean estimates from many cruises going back to like 1990, especially at Trinity West. There are, I think, almost 30 sections by now which are building this mean. So quite a huge effort to build these 3 plots in the end. So at 5 South, it's very similar to 11 South. So you have this western boundary circulation and both AMOC branches indicated here. At 35 West, it's quite interesting because you have, on the one side, you have the western boundary circulation, but on the other side, you also include the equatorial circulation. So this is also important to know for the next few slides. And at 23 West, it's nice to see these equatorial current systems, which especially manifest in these zonally alternating currents at intermediate level. Okay, and these are now especially important to use because, as I said, there's no geostrophic balance at close to the equator where the Coriolis parameter vanishes. So we would have huge gaps when we would have used the Argo data. So this is why we are now using ship-based measurements. And then we came up with another schematic for all these different transport estimates at all different locations. And we divided these estimates into an upper layer, which is composed of these 3 water masses here. And in green, you can just see very schematically the South American coast and then the African coast. And then the red lines indicate where we used Argo data, and the black lines where we used ship section data. Okay, so just walking through this plot. In general, the water entering the tropics in these upper layers is very concentrated to the western boundary, so where 15 square drops enter, and slightly intensified at 5 south, but also partly recirculated at 5 south further offshore. Then across 35 west, we observed about 7 square drops going westward and along the coast. But then again, remember that 35 west is just a mean of the western boundary circulation and the equatorial circulation. Then further north, about 6.7 square drops are observed to leave the inner tropics at the western boundary, and then we have this reflection into the tropical Atlantic, where we see the big contribution due to the equatorial undercurrent. So remember, now at 23 west, we don't have we're not having this compensation due to the western boundary component. There's just the equatorial system, and this is then in these layers especially largely dominated by the equatorial undercurrent. But just to mention these mean values at 35 west and 23 west, behind these mean values, there's actually a huge amount of zonal exchange of mass. So something more than 20 spare drops going into both directions. And yeah, just to give some more insight on these zonal exchanges in the tropics. And then in the end, across 10 south, 11 south, and 10 north, interior and eastern boundary parts, there's mainly southward or basically poleward transport, which is mainly driven due to Ekman transports in the surface layer. Okay, so this is the schematic for the upper layer. Now we did the same for the intermediate water layer, which is a bit different. That's why we came up with a different one for the intermediate water. What is the same is that it's also concentrated at the western boundary, the inflow. Basically the same at 5 south, but again also some recirculation further offshore. There's a strong westward or northwestward transport across 35 west that is also supplied by the equatorial intermediate current. And then at 10 north western boundary, about 10 square drops are leaving the tropics, and not much transport observed in the interior. Interestingly, there's some recirculation of intermediate water, which is then again supplying the tropical intermediate or the equatorial intermediate current system. But then again, there's huge amount of zonal exchange and recirculation within these tropical bands and across 23 west. All right, and this leads me now to the last plot actually. So just a summary plot of all layers, and in total the AMOC return flow from Argo observations. So the mean velocity for this layer, including these 4 water masses, is shown in the colors. The meridional transport in the color shadings, and the horizontal component, so zonal and meridional in the arrows. And clearly seeing this concentration of flow at the southern part or the southern section, and then once it crosses the equator, you still have this steady western boundary current, but also this very obvious reach reflection going to the NECC, and what's not be seen from this Argo data in the EUC. Okay, and then so across 11 south and 10 north, we have something like 16 to 17 spare drops of net northward transport, so very similar to previous estimates. And we also, at the Argo sections, we divided these transports again into a geostrophic component and an Ekman component. So these values are showing both, but these tables now just just dividing these transports, because it shows that at the north, as I said, there's not only the western boundary route, but there's also this interior route, which is then also largely driven by Ekman transport. So there's only surface water now that is leaving the interior part. Okay, so then just a few key points. So we are really happy that the Argo data, the high resolution Argo data, is showing good agreement with ship-based measurements at 11 South for the upper 1,200 meters, because so far in previous studies there were some troubles with Argo data at the western boundary. Then we've seen that the diapignal transport into the STC layer and the tropics is roughly about a third of the previous estimates. So this could be quite an important term or is an important term in STC estimates, and likely due to the high resolution now it's lower than previously estimated. And with all these different sections and Argo data, we try to come up with a coherent picture, or as coherent as possible from Argo data, about the AMOC return flow. So this is something that's so far has been largely seen in Lagrangian model studies, or using drifter data for the surface parts. Okay, and then just if you're interested in subtropical cells, because I did a lot on this during my PhD. The first part that I showed is based on this paper here, deriving the mean state of the STCs from Argo data, but also from reanalysis data and further data products. And then we also found a connection between the transport variability of these STCs to SST variability in the equator. So something that has been shown a lot for the Pacific Ocean, but also now for the Atlantic Ocean on these longer time scales. There's some connection. And it's not only SST, it's also interesting for the STCs are also playing a role for the EOC. And what we found in a more recent study was that we observed an undercurrent intensification, quite strong one of 20% during 10 years. And we concluded that this intensification must be due to a change of trade winds in the Northern Hemisphere. And what we also see is that the Northern Hemisphere did spin up quite a lot during this period. And then this is what we think the connection mechanism between the intensified trade winds and the strengthening of the EOC. So just want to make a point that the STCs are quite important, at least I like to believe that. And with this, I thank you for your attention. Want to take the chance to thank all the scientists and technicians who did a lot of work for these shipboard measurements, all these ship sections, as I said, over the last 30 years. And also without the Argo program, these kind of studies, they would have not been possible, and my whole PhD would have not been possible. So big thanks also to them. And I think since this is being recorded, I just click one short time to the references, and so that everyone can look at them in the video. Okay, that's all. Thank you.